There's like the bottom.
Oh, yeah.
There's like the top vertex.
Yeah,
They all go up.
You don't.
Pretty sure it's
Yeah. So I need 6 altogether. I have all 6. So I'm actually done.
Yeah, I don't know.
Oh,
That's a bit better.
yes. So that one's chill. This is where it starts getting hard, in my opinion. The dodecahedron.
I don't know. I think it's really
Oh. Really?
But like, you can just like look at it. Like, I don't know how to do it. But it's not only 6 pieces. But there are only 6.
Yeah, you were telling me that there were more. You were confused.
Yeah, it's confused.
This one has inverses. Oh, yeah. 20? Yeah, of course there are. 5, and then 10 more. So it needs 20 inches. We need 5 more vertices. No, 10 more. I think like, I think it's, you want like an upside down one too.
Is this a net? No, it's not, it's not.
Could be worse.
Oh my.
Yes, and then I get my 12 now, right? It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
It's like, what do you look at it
I did this like third period and I still find it hard. I also did it last year over and over again. The icosahedron took me like 20 minutes the first time I tried to do it. But anyway, this is really cool. All right, 10 minutes. We're going to do 2 things. One, we're going to prove Euler's formula. Ready?
Drawing my dodecahedron.
Okay, instead of proving the theorem about polyhedra, because that sounds hard, I'm going to prove it about planar graphs. Because every polyhedron can be turned into a planar graph by removing one face and stretching it all out. Okay, so here is the theorem. So let G be a connected planar simple graph with epsilon edges and n vertices. You move the camera? Okay. Okay. Let rho be the number of regions in a planar embedding of G counting the outside region as 1. Counting the outside region. Okay, so G is a connected, planar, simple graph. What does it mean to be planar? It means that there exists a planar embedding. So take one of those planar embeddings and let rho be the number of regions, counting the outside region ones.
How do you know rho is unique?
How do I know rho is unique? Yeah, I don't. I haven't given any justification for that. Good question. I don't know. But I guess what's interesting to me is that the polyhedron sort of is sort of associated with the particular planar embedding. So it's a good question, but it's not directly relevant to me at the moment because I claim that there's a direct relationship between a particular planar embedding of a graph and the corresponding polyhedron. Do you agree with that?
There's only one way to draw.
Because there's just really only one way to take a face out of a polyhedron and spread it out. I guess that's not even true, right? Because it depends on which one you take out.
No, they're all the same.
But they're kind of all the same.
Well, not if they're different.
This is another one of these weird theorems which kind of transcends like 3D geometry and also graph theory. I don't have an immediate answer to that. I appreciate the question. Okay, so what are we going to prove? We're going to prove Euler's formula for this graph. And so what we're going to prove is that rho, the number of regions in the planar embedding, including the outside one, is equal to the number of edges of the graph minus the number of vertices plus 2. This is the claim. Alright, and so we are going to do this by induction. And there's really like one sort of claim which is kind of important, which is given any graph, there are different ways in which I could build the graph up. So okay, take the planar embedding of the cube, for example, right? Because I'm going to prove this theorem by induction, or I intend to prove it by induction, right? So if I'm going to prove this by induction, then I need to somehow induct on the number of edges. What's up?
I don't pass 50.
Do you have a pass? You have to go somewhere.
Sure, take a bus stop. Sure. It's only like 8 minutes.
Only 8 minutes. We better hurry. Okay, here's a cube. So I want to prove that this particular planar embedding has this property. And by the way, it just does because look, there are 2, 4, 5, 6 regions, and however many edges, blah blah blah. Okay, we confirmed that already. With the cube itself, it's the same thing with the planar embedding. So I want to build this up edge by edge, and I essentially want to show that that like rho plus and minus epsilon equals 2. This is kind of a no secret. We're talking about with like invariance. If I can show that these 3 always add up to 2, or add up to, you know, these 2 added minus this one is always 2, then I'm good to go. So I want to kind of add an edge each time in such a way that and I want to show that that relationship continues to hold. I mean, that's really the gist of the proof. But if I have a graph, I need to build it up like in an intelligent way. I can't just build it up like weirdly, because then I might get like disconnected stuff. So like this would be like a crap way to build this graph. Like this and this and this and this. And then this and this and this and this. Like I don't want to do it that way. I want to do it in such a way that as I build up edge by edge, the graph I have so far is connected. Does everyone accept that this is possible? I guess my argument would also like depend on some kind of algorithm, like just start at a certain point and just add an edge and then add another one and add another one and add another one and keep doing that, like staying connected the entire while, and then that is like possible to do. Yeah. Does everyone accept that? Okay. All right. So if you accept that, then that is exactly what I want to do. Label the edges of G in such a way, like E1, E2, all the way up to E epsilon, that the subgraph of G created by adding edge is connected. Label the edges of G.
Aren't subgraphs defined off of?
In such a way, E1 through E epsilon, that the subgraph GK composed, the subgraph GK of G composed of edges 1 through EK is connected. What's wrong?
Nothing.
I think it's okay, right? Have we ever written this? Yeah. Label, so basically construct some sort of sequence of edge additions in such a way that you remain connected the entire way. And denote GK, the subgraph of G, when you've added the first K edges. Cool? I think I said this correctly. So is connected. Okay, good. All right, and just a little bit of notation. Let GK have epsilon K edges, NK vertices, and rho K regions. All right. Good. Good. All right. So now we're going to start building G, one edge at a time. This is now the easy part that just makes sense. So, all right, consider what does G1 look like? Well, G1 is going to be the graph just with a single edge, edge 1. What is epsilon 1, the number of edges in this graph? 1. What is N1, the number of vertices in G1? 2. And what is rho 1, the number of regions in this? Just 1, it's just the whole plane. Okay, cool. Does this satisfy the property? Rho 1, does rho 1 equal E1 minus N1 plus 2? Well, yeah, it just does, right? Because 1 is 1 minus 2 plus 2. Okay, so this is good. All right, base case number 1 complete. Okay, consider subgraph G2. This is the graph that results from adding edge 2 to edge 1 in such a way that G2 is still connected. That's crucial. What is epsilon 2, the number of edges? Well, that's 2. What is N2, the number of vertices? 3. What is rho 2, the number of regions? Still 1. And so what have I just done? I've just added an edge and a vertex. If I add one of these and one of these, then the right-hand side of the equation is staying constant. Cool? Okay, so those are my 2 base cases. All right, now comes the inductive step. So now suppose, this is my inductive hypothesis, suppose that subgraph G sub k minus 1 satisfies the formula. Satisfies the formula. In other words, suppose that rho sub k minus 1 equals epsilon sub k minus 1 minus n sub k minus 1 plus 2.
0 versus 1 edge and 1 edge.
Now we're just going to do, are we good? Yeah. Clarifying question?
No. Now we're just.
Okay, okay, so now consider graph G sub k. Well, what are the possibilities? There are really only two possibilities. You have some subgraph, G sub k minus 1, and I'll draw 2 pictures because we're going to sort of do this twice. And who knows exactly what it looks like, whatever. Okay, time to add another edge to make graph GK. Well, one possibility, the graph has to remain connected. So I can't make a new edge that's just floating out in space, right? So I really only have 2 possibilities. What are the 2 possibilities?
You add another vertex or you don't.
I either add another vertex and my new edge connects my new vertex, so this would be edge K. So I either add a new edge by creating a new vertex and connecting that vertex to one of the previous vertices, or I connect to vertices that are already in the graph. Okay, and I claim both cases I have this sort of preservation of this formula. Because here, well, what just happened? What is the relationship between the, okay, well, let's just do it. What is E sub k?
E sub k minus 1 plus 1.
Yeah, it's going to be E sub k minus 1 plus 1, because of course all I did was to add an edge. What is N sub k?
N sub k minus 1 plus 1.
Yeah, I added a single vertex, right? So it's going to be N sub k minus 1 plus 1. What is rho sub k?
Rho sub k minus 1.
Yeah, it's going to be rho sub k minus 1. No, it's just rho sub k plus 1. It's just still the same. No new regions have been created. Right?
Oh, rho sub k minus 1. Yeah.
Rho sub k. Yeah, and so what have I done? I've added 1 to the number of edges, and I have added 1 to the number of vertices. So these that cancels each other out, and therefore the formula still holds. Cool?
Yeah.
Okay? How about the second case? And you have to be, what's up? I have used, when have you're saying not use planarity?
Well, you have to use planarity for that sense.
At this moment, you have to use planarity, for sure. Because you can only say that you haven't created a new region because the graph is planar. So adding this new edge can't interfere with any of the previous edges. So no, yeah, that's important to mention. Yeah, it is this, I think you're saying this is the only moment where I'm using planarity. I guess over there I will too. But because it's planar, this new edge doesn't do any funny business with any of the previous regions. It can't, because the graph's planar. Okay, la 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 la. Good. So now if I create a new edge, right, the picture just sort of is like doing the proof for us a little bit, but if you want to be a little bit more careful about this, note that this graph being connected means that this new edge I created, EK, suppose this is connecting V1 to V2. Well, I claim that since V1 and V2, so since G sub k minus 1 was connected, that means that there was already a walk from V1 to V2. As there was already a walk, this new edge completes a circuit. And that new circuit induces like a new region. So common sense is a new region is created, but I think it can be even more formal about that. All right, and so let's just go through them. What's E sub k? Well, it's just E sub k minus 1 plus 1 again, because of course I added an edge. That's what happens at every step. N sub k is, did I add a new vertex? I did not. Yeah, so this is still N sub k minus 1. But rho sub k is rho sub k minus 1 plus 1, because I did add a new region. And therefore, what I have done, again looking at the formula, is I added 1 to the number of edges and I added 1 to the number of regions, so the equation remains balanced. Yo.
Why do you need 2 base cases?
I don't know. Maybe I don't.
No, because the second case follows from the second base case, right?
I guess it's a little prettier because this case can't even happen yet until we hit G2. I don't know, but maybe I didn't use both. It helps to get things going. All right. So is there anything else to say? No. It holds by induction. All right. That's pretty great. I should mention that this is like the history of this theorem is really awesome and outrageous. There's an entire book called Proofs and Refutations, and it is very, very interesting. It is by I forget his first name. I think it's Imre Lakatos, but I could be wrong about the first name. This Hungarian mathematician, and it is like, for those of you who took logic, it is in some ways kind of a perfect sort of sequel to everything we did in logic. It assumes already that you have like a full and complete philosophical understanding of all the development of math and what math means and what it is. And the entire proof is like a 150-page conversation, sort of Platonic dialogue between this guy and this entire class full of people. And they go through Euler's formula, and they sort of give a proof of it, and then someone criticizes the proof, and then someone says, oh, okay, and then they have these like very interesting mathematical, philosophical fights about what math is and whether these protests are like worth or should just be blown off, or whether we need to modify our definition. You can keep modifying the definition and modifying and getting more and more proofs. So this is like the most basic proof. I think this is the one that Euler himself did, but then the proof just gets continued, and then there is some sort of polyhedron which just don't satisfy this Euler's formula, including like so-called star polyhedra. Although I might be like wrong. I'm starting to forget what happens. But if you allow like an edge to go like through multiple vertices, then it sort of doesn't work anymore. And this entire thing eventually gives rise to like the birth of like kind of topology. Comes from trying to classify. Sort of don't know totally what I'm talking about, but I think this is right. Classify shapes by what that extra number 2 is. So for polyhedra, the answer is 2. But for like a torus, it's not 2, I think. Is that true? I actually don't know. I think for a torus, I think for a torus, you get that it's not true.
It doesn't even have like.
Like take a torus made out of like rectangles. Do you get f equals e minus v plus 2? I think you don't. You guys understand what I'm talking about?
Like,
Make like a torus shape, but out of like,
You mean like that
not
pentagon?
rectangles, like out of like rectangular prisms.
You mean like
It would have 16 faces, I think.
No, but like,
Yeah,
it's,
six-
in other words, there's a
16
hole in the
faces.
middle. So it's,
Yeah,
make,
say like
make a
16
polyhedron in the shape of a donut.
I mean like the pentagon in like DC, like
Wait,
pentagon.
Oh, like the pentagon in DC, yes,
16.
exactly.
Oh,
I think it violates this. And because it's topologically different. I don't really know what I'm talking about. All right, goodbye, internet.